This practical is a classic demonstration of chemical kinetics, and it's called the iodine clock reaction. So what we have here is hydrogen peroxide that has been acidified reacting with iodide ions to produce iodine and water. But also in that mixture we have thiosulfate ions, and the thiosulfate ions will react with the iodine to produce iodide ions again. Now, another thing we have in the solution is some starch, and what happens is as soon as all of the thiosulfate ions run out, the iodine will no longer be converted back into iodide, meaning that we're going to end up with iodine in our solution, which in the presence of starch gives us that blue-black color. So the solutions, they're all colorless, and when you add them together, the whole time the reaction's ongoing, it remains colorless. But as soon as the thiosulfate runs out, and there's iodine now present in the solution that's not being broken down into iodide, then it suddenly indicates with the starch to give you that very sudden change to blue-black. Now, this is a really useful reaction because it allows us to investigate the effect of changing concentration of a particular reactant on the rate of the reaction. So what we're going to do here is we're going to set up the reaction with some hydrogen peroxide, some sulfuric acid, a little bit of distilled water, starch, potassium iodide, and sodium thiosulfate. And we're going to time how long that takes before the blue-black color appears. And then we're going to repeat the experiment using the same concentrations of all of our reactants, but varying the concentration of just one. We're going to vary the concentration of the potassium iodide. And what we'll be able to see is the effect changing the concentration of that one reactant has on the overall rate of the reaction. So to start with, we've measured out 10 centimeters cubed of hydrogen peroxide. That's going to be the last thing we're going to add because that's going to kick off the reaction. All of these other reagents together won't react. So we start off with 25 centimeters cubed of sulfuric acid, 20 centimeters cubed of water, approximately a centimeter cubed of starch solution, and just the 5 centimeters cubed of the potassium iodide and 5 centimeters cubed of sodium thiosulfate. Okay, that's 5 of the potassium iodide, and now we need to add 5 of the sodium thiosulfate. Okay, so now we have all the reagents we need in there, apart from the hydrogen peroxide. So again, just to recap, the hydrogen peroxide is going to react with the potassium iodide to produce iodine, but the iodine immediately reacts with the sodium thiosulfate to produce iodide. And once this runs out, once the sodium thiosulfate runs out, then there will be iodine left in the solution, which will indicate with the starch, and we'll get that sudden change to blue-black. So we're going to add our hydrogen peroxide, start the timer, and give it a quick swirl. And then we're just going to time how long it takes until this solution changes color to that dark blue-black. And there we have our very sudden color change. It went from being colorless to this very, very dark color, and it took 53 seconds. Now, all we're going to do now is repeat this experiment, keeping the concentration of everything else the same. So it's important that the total volume of our solution remains the same. That's the purpose of the water. So as we start to add more potassium iodide, we're going to keep the same volume and concentration of thiosulfate, starch, sulfuric acid, and hydrogen peroxide. But as we increase the volume of the potassium iodide, we need to decrease the volume of water we're adding so that the total volume remains the same, so that none of the concentrations of any of the other reactants change, only the potassium iodide is going to become more concentrated, which means that the rate of reaction is going to increase, and then we should be able to see the effect the change in concentration of potassium iodide has on the rate of reaction, and then we can determine whether the potassium iodide is a zero order, first order, or second order reactant. Now we have some results. We can begin to look at the effect of changing concentration of potassium iodide on the rate of the reaction. Now, before we can do that, we need to actually calculate what the concentration of potassium iodide was in the solution. We know the concentration of potassium iodide we started with our stock solution, and we know how much we added in each experiment, but because you're adding it to other aqueous solutions, you're actually diluting it every time. So what we need to work out first is how many moles of potassium iodide did we actually add. So we're going to be working out the number of moles using moles is equal to concentration times by volume, and remembering that volume in this equation is always measured in decimeters cubed. So for the first one, the concentration was 0.1 and the volume was 5 centimeters cubed. Now, to convert from decimeters cubed to centimeters cubed, you simply divide by 1,000, because 1 decimeter cubed is equal to 1,000 centimeters cubed. So if you want to go from centimeters cubed to decimeter cubed, you just divide by 1,000. So for our first one, it's going to be 0.1 times 0.005. Giving us the number of moles of 5 times 10 to the minus 4. The second equation, we're going to use the same equation, but we're going to substitute in different values because we had a different volume. Still 0.1, but this time 0.01 decimeters cubed, giving us 1 times 10 to the minus 3, and then 0.1 times 0.015, giving us 1.5 times 10 to the minus 3, 0.1 times 0.02, giving us 2 times 10 to the minus 3, and 0.1 times 0.025, giving us 2.5 times 10 to the minus 3. So that is the number of moles we added to each one of these experiments, experiments 1, 2, 3, 4, and 5. And all we need to know now, if we want to know the concentration of potassium iodide in the solution, we need to know how many moles there were, which we do now know, and what the total volume was. So each one of those experiments all added up to 56 centimeters cubed. So the total volume was always 56 centimeters cubed, because we use the exact same volume of sulfuric acid, hydrogen peroxide, the sodium thiosulfate, and starch. And all we varied was we increased the volume of the potassium iodide, but at the same time we decreased the volume of water, keeping the total volume the same. So in order to get the final concentration of potassium iodide in the solution, we have to divide the moles by the total volume. And again, that's in centimeters cubed. We need it to be in decimeters cubed, so you divide by 1,000, giving us 0.056. So the first one, 5 times 10 to the minus 4 divided by 0.056, giving us a value of 8.9 times 10 to the minus 3. 1 times 10 to the minus 3 over 0.056, giving us 1.8 times 10 to the minus 2. 1.5 times 10 to the minus 3 divided by 0.056, giving us 2.7 times 10 to the minus 2. 2 times 10 to the minus 3 divided by 0.056, giving us 3.6 times 10 to the minus 2. And finally 2.5 times 10 to the minus 3 divided by 0.056, giving us 4.5 times 10 to the minus 2. So we now have our values for the concentration of potassium iodide in each one of those solutions. The other thing we need to compare that to is the rate. Now, we didn't measure rate, we measured time taken. In order to get the rate of a reaction when you are looking at the time it takes to finish, you can quickly convert that to rate by doing 1 over time. So if the time was 54 seconds, 1 over 54 gives us a rate of 1.9 times 10 to the minus 2. Okay, so I'm just going to make a note of that down here. So rate is equal to 1 over time, giving units of seconds to the minus 1. For the second experiment, 30 seconds, so 1 divided by 30, 3.3 times 10 to the minus 2, 1 over 20, 5.0 times 10 to the minus 2, 1 over 15, 6.6 times 10 to the minus 2, and finally 1 over 12, 8.3 times 10 to the minus 2. So now we have concentration of potassium iodide and rate of reaction. So if we plot those against each other, we will be able to determine whether it is 0, first or second order. So we're going to plot our concentration of potassium iodide on our x-axis and the rate of reaction on the y-axis. And what we're looking for is the relationship between those. If there is no relationship, then it is zero order. If there is a directly proportional relationship, then it is first order. And if there is an exponential relationship, then it is second order. So here we have the graph plot. Now I've included the standard form into the axis just to make the axis labels easier. It makes the whole thing easier to plot. Rule of thumb when you are plotting a graph is you want your plots to take up at least half of the space provided. Okay, so that's not necessarily the graph has to take up half the space, but the actual plots themselves have to take up at least half. So the first one we are plotting is 1.9 times 10 to the minus 2 against 8.9 times 10 to the minus 3. So, got a plot there, plot here, plot here. And straight away, what we should be seeing is that this is a nice linear relationship. So if we grab our ruler, we should be able to draw a nice straight line of best fit through all those plots. It's never going to be perfect. This was a particularly hot day, so there's quite a bit of variation. But there is our line of best fit. So that's a pretty clear linear correlation. So our justification then is there is a linear correlation between concentration of potassium iodide and rate. Therefore, rate is equal to change in potassium iodide concentration to the power 1. Therefore, potassium iodide is first order.